thanks to the organizers for the invitation, and also thanks for running the seminar series in general, which has been fantastic. So I wanted to, the goal for this talk is to try to explain sort of the relationship between three different types of objects, which is sort of a picture that's emerging, which I think is kind of intriguing. So on the one hand, what I'll talk about first is singular rational plane curves. So this is kind of a classical topic in algebraic geometry. So just basically curves in CP2 of genus 0 with some singularities. And on the other hand, there's the SFT symplectic field theory, specifically in this talk for just the symplectic field theory of four-dimensional ellipsoids. And then finally, there's this notion of stable symplectic embeddings. And for this talk specifically, we'll be concerned with embeddings from a stabilized four-dimensional ellipsoid into another four-dimensional ellipsoid. So basically, you look at symplectic embeddings from kind of something of the form ellipsoid cross Cn into another ellipsoid cross Cn. And so my goal is to try to explain sort of the connection between these three topics. So I would say the connection between maybe 2 and 3 is already fairly well established at this point. So the rough idea is that symplectic field theory can be used to define symplectic embedding obstructions, and specifically there's kind of a part of SFT which gives stable obstructions, so kind of dimensionally independent obstructions. Although it gets into all sorts of interesting questions about actually kind of understanding the SFT of ellipsoids, which is itself a pretty subtle question. I mean, it gets into all sorts of interesting enumerative problems, which I'll talk about a little bit. And so my main goal is to kind of maybe explain how one fits into this story. So try to argue that that sort of understanding the SFT of four-dimensional ellipsoids is closely related to kind of classical questions about understanding the existence of plane curves with certain singularities. Okay, so let me try to start by talking a little bit about just singular algebraic curves in general. So this is, for some people, pretty classical, but so the setting is just, consider a homogeneous polynomial in 3 variables. So then you can look at its vanishing set, V of f, and this gives you an algebraic curve in CP2, possibly with some singularities. And remember that, so to find the singular points, you just look at, so a point in projective space in CP2 is a singular point if basically the derivatives of the defining polynomial vanish at that point. So the partial derivatives vanish. And so given a polynomial, you can just check where, what the singular points are. And specifically, we might as well assume by some change of coordinates, we could just assume that we're interested in the point 0. So 0 lies in our curve. And then we can just, reduce f to a function of 2 variables, just in kind of the affine chart where z is equal to 1. And well, you can write, so you could write f, you could sort of expand f as sort of a degree m homogeneous part, and then a degree m plus 1 homogeneous part, up to degree d homogeneous part, where d would be just the degree of the polynomial, or the degree of the curve. And here m, so m is kind of the smallest, basically the smallest exponent that appears in the kind of polynomial expansion. So, and this is called the multiplicity of the curve at 0. So the multiplicity, another way to think about the multiplicity is that it's kind of the multiplicity of a curve at a point is the smallest intersection number of the curve with any divisor passing through that point. So if the multiplicity is m, that means that any other curve passing through that point intersects your curve with order at least m. And so a point is singular if and only if the multiplicity is at least 2. So if it's a smooth point, then the multiplicity is just 1. Otherwise, the multiplicity has to be at least 2. So maybe let me just give some kind of simple examples to get a feel for what kind of singularities can occur. So maybe the simplest singularity would just be the ordinary double point. So this is just, if the polynomial were x squared minus y squared, you basically just get, 2 branches. You get the x-axis, the y-axis, and the x-axis, and they just meet at the origin here. This is called an ordinary double point. But this is actually, so there's actually 2 branches passing through the origin, because this is actually a reducible polynomial. You can factor it, and so this is kind of what I would call a multi-branch singularity. So there's kind of, in fact, each branch is actually smooth, but you have 2 different branches meeting at a point. Okay, so on the other hand, so here's kind of the simplest example of a unibranch singularity. So one which, only has 1 branch passing to the point, or equivalently, which is sort of locally irreducible near the origin. So this is called the ordinary cusp. So in this talk, when I say cusp, I mean not ordinary cusp. Sometimes when people say cusp, they mean ordinary cusp, but here there'll be more general cusps. But the ordinary cusp is just modeled on x cubed equals y squared, or like the sort of semi-cubic parabola. And then it has a singular point. It has a single singular point which has multiplicity 2. So basically any curve passing to this point will intersect this curve with multiplicity at least 2, possibly more. For example, if the curve were sort of in this direction, then it would actually have higher multiplicity. But okay, and this generalizes to what I would call the PQ cusp. So the PQ cusp is modeled on x to the p equals y to the q. So I'll usually assume, I guess I'll usually assume that p and q are relatively prime. So GCD of p and q is 1. And I'm usually thinking of p as being bigger than q, although there's kind of a symmetry which says that p and q are on equal footing. So this is sort of a generalization of the ordinary cusp, and I'll denote this singularity by CPQ. And it's not difficult to see that this, so you can look at the link of the singularity. So basically, if you take this point and then you look at a small ball around this point, a 4-dimensional ball, then the intersection of this ball with the curve will be basically a knot in S3. So it would be sort of like the intersection of this curve with the ball, or rather with the small sphere, and in fact, the link of the singularity essentially determines the singularity, and in the case of a PQ cusp, it's just a PQ torus knot. So at least up to homeomorphism, you can think of this singularity as just being the cone over the PQ torus knot, but it's better to just remember the link. Remember that the link is a PQ torus knot. And this is, so one way to think of the PQ torus knot is it's kind of what you get by taking a certain braid closure where you have P strands and then you do kind of Q half twists. Okay, so this would be like the 4-3 torus knot. And there's kind of so this is just kind of a local singularity, but there's also a global version of this curve. So if you look at if you just take basically the projective closure of this polynomial, so you get this, so now you get a homogeneous polynomial in 3 variables. And this thing actually, so this has the singularity at the origin, but it also has one other singularity. So it has a singularity at 0, 0, 1, and also a singularity at 0, 1, 0. At 0, 0, 1, it's just the PQ cusp, and then there's actually a P minus Q cusp at the other point. And also, so it's useful to note that this is actually a rational curve. So rational curve basically means that you can parameterize it by a rational function. So in this case, there's just kind of an easy way of parameterizing the curve by a copy of CP1. Okay, so or geometrically rational means basically genus 0. So I'll mostly be interested in rational curves in this talk. Okay, so here's a more complicated polynomial. So just some, I guess, degree 7 polynomial and 2 variables. So in general, there's when you're given a polynomial, so and it has a singularity at the origin, or at least it contains the origin. So there's an algorithm which allows you to kind of understand the singularity at a given point, which actually I think goes back to Newton. So it's called the Newtonprisso algorithm. And basically, the Newtonprisso algorithm gives you a way to parameterize it gives you a way of kind of locally parameterizing the curve near the singularity. And in this case, it spits out a parameterization like this. So the x coordinate is parameterized by t to the 4th, and the y coordinate is parameterized by t to the 6th plus t to the 7th. And from here, you can get the so-called Prisso parameters. So basically what you do is, so if all of these exponents appearing here were a multiple of 4, then this would actually just be smooth at the origin. Okay, but it's not smooth because these are not all multiples of 4. So you look at the kind of the first exponent, which is not a multiple of 4, which in this case would be just 6. And then you kind of write 6 over 4 in kind of reduced fraction terms. So 6 over 4 is 3 over 2. And then you say that P1, Q1 is the first Prisso pair. Okay, and then if all the remaining exponents were a multiple of Q1, which is 2, then there would only be one Prisso pair. But in this case, that's not the case. So rather, the next term would be 7 over 4. So then you try to write this. You write 7 over 4 as P over Q1 times Q2, where Q2 is some new denominator. Q1 was 2. So then this tells you that P2, Q2 is 7 over 2. Well, I should say PQ, Q2 is 7, 2. So that would be the second Prisso pair. And the general picture is that when you always have a finite, so you always have a finite number of Prisso pairs, and then they basically describe the and let's assume now that it's a unibranch singularity, which is, by the way, just what when I say cusp, I just mean a unibranch singularity, so locally irreducible. So then the picture is that at any sort of unibranch singularity, the link is a iterated torus knot. So it's kind of a cabling of torus knots. So in this case, you have 3, 2 and 7, 2. So you have the 3. So here's the 3, 2 torus knot, which is the trefoil, but then you take a cabling over that, which is the 7, 2 torus knot. So then you have sort of the 7, 2, sort of, you look at the first torus knot, and then you look at a tubular neighborhood, and then you take a torus on the boundary of that tubular neighborhood, and that gives you a cabling. And in principle, you kind of keep going. Okay, so this describes the link in general. So in this talk, I'll be mostly just thinking about the case where you have only a single Prisso pair. So then basically we're just looking at singularities, which are cones over torus knots. Okay, but this is just so indeed any unibranch singularity is kind of given by some kind of iterated torus knot. Okay, and another kind of important way of understanding singularities is by resolving them. So resolution of singularities. So in the case of plane curve singularities, resolution of singularities is basically what you do is you basically just keep blowing up. You keep blowing up the singular point until it goes away. And since we're in complex dimension 2, you just have to blow up at points. So let me just explain how this works, maybe with an example. So supposing you started out with a curve with a 5, 2 cusp. Okay, so this is like a PQ. So think of this as like CPQ. And so after you blow up, you get a milder singularity, which so this becomes a 3, 2 cusp. So basically, you replace PQ with C P minus QQ. Okay, so but it's still singular, but it went from a phi2 cusp to just an ordinary cusp. And you pick up this exceptional divisor E1, and then you can blow up again. And when you blow up again, you actually, so now you get you get a C, you basically get a C 2-1, which is just a smooth point. So it's already smooth. And now you have two exceptional divisors, E2 and the proper transform of E1, so which is in homology class E1 minus E2. Okay, and this thing in some sense you're already done. So this is called the minimal resolution. So the proper transform of the curve is now already smooth, but sometimes it's also natural to keep going because the total transform, so the collection of the curve and also all exceptional divisors you introduced is not a normal crossing divisor yet. So the curve is actually tangent to this exceptional divisor. So you can keep going until the total transform is a normal crossing divisor. So blow up one more time. So the curve is already smooth, so it's still smooth, but now you get a curve in the class kind of C minus 2E1 minus 2E2 minus E3. And you still have a triple intersection point here, but then you blow up one more time, and then finally you get a normal crossing curve. So this is called the normal crossing resolution. So it takes place a little bit later than the minimal resolution. Okay, and kind of more abstractly, the picture is that you start out with a singularity. So you start out with some curve with a singularity, and then you resolve, and then after resolving, you get its proper transform C tilde, along with some other collection of curves, which you could think of as like a plumbing. So in this case, you have the orange curve, the red, the green, and the purple, and then it's locally it's a plumbing, and then locally you can just describe it by the self-intersection of each of these curves. So like this is an exceptional divisor, has self-intersection -1. The red curve, for example, has self-intersection -3. So I've just labeled each component by its self-intersection number. Okay, so you replace a single singular curve with sort of a plumbing diagram where each component is smooth. Okay, and this is the picture in general. So you start out with a PQ cusp, you kind of resolve it into some plumbing diagram where the sort of weights of so you always have this picture where you have sort of a single -1 curve, and then there's kind of two branches, sort of a top branch and a bottom branch, and the weights -A1 minus A2 etc. and -B1 minus B2 etc. are given by they're sort of related to continued fraction expansion. So specifically, these are given by the negative continued fraction, the coefficients of the negative continued fraction expansions of not quite P over Q, but some fractions which are derived from P over Q. So Q prime is basically the inverse of Q mod P, and P prime is the inverse of P mod Q. So they're given by these conditions here. And then you look at these fractions, and then you take their negative continued fraction expansion, which means you put minus signs instead of the usual plus signs here. And then these coefficients tell you what kind of plumbing diagram you'll see in the resolution. Any questions, by the way? So feel free to just interrupt me at any moment. Okay, so, well, kind of a basic question, which is, I think, still kind of very much an active area of research, is just, in general, what kind of singularities can a degree D rational plane curve have? So in other words, so the most basic form of this question is just, if I give you a degree like 17, can you give me a list of all possible combinations? And let's assume maybe, we're only interested in, so first of all, you could ask the question, if you're just only allowing cusp singularities, maybe only cusp even with one Pusso pair, and then you can ask kind of what possible combinations of Pusso pairs could be the singularities of a degree D curve. So there's kind of one really basic obstruction to having a degree D curve with certain singularities, which is given by just the ejunction formula. So the ejunction formula just says that basically each singular point contributes some amount delta of p to the kind of total count of singularities, and this has to add up to d minus 1 times d minus 2 over 2, which is the term appearing in the degree genus formula. So for example, if the degree is 1 or 2, so a line or a conic, then you're not allowed to have any singularities. And in general, the contribution of an ordinary double point is 1, and the contribution of a PQ cusp is p minus 1 times q minus 1 over 2. Okay, so this is consistent with the fact that if q were 1, then this is just 0. So a p1 cusp is just really just a smooth point. But on the other hand, the ordinary cusp, so p equals 3, q equals 2, contributes 1. So it's sort of a simplest possible singularity, which is unibranch. Okay, so for example, if in degree 3 you're allowed to have one singular point, and so basically the possible degree 3 curves are either a smooth degree 3 curve, which is just a smooth elliptic curve, or you could have one ordinary double point, or you could have one ordinary cusp. And this is the only case which would be so this is genus 0, and this has geometric genus 0, I think, but arithmetic genus 1. So if you could, so this we will consider this also a rational curve, because you could sort of parameterize it by a CP1 where you just kind of ignore the fact that you had that double point. Okay, and then there's various kind of more sophisticated obstructions, which I'm not going to say very much about, but so for example, there's very strong obstructions coming from like Heegard-Floer homology, or even involutive Heegard-Floer theory. So there's one called the semi-group obstruction, which is quite strong. There's also obstructions coming more from algebraic geometry. So there's what's called the semi-continuity of the singularity spectrum. And there's various other obstructions that are quite strong, which go beyond the ejunction formula. So let me just try to give sort of a small sample of the kind of things that are known. So this is very far from being representative, but so I believe up to degree 7, there's just a kind of complete, at least in the case of only cusp singularities, there's a complete list of what types of curves can occur. Basically, because the degree is small, so there's kind of a limited number of singularities you can have. So you can sort of, I mean, the number gets pretty large, but you can sort of write down all possibilities. And I should apologize right now, because I'm not really going to be able to give proper attribution. So there's many people have worked on this this type of result. So unfortunately, I'm not going to be able to give good attributions here. But let me mention one sample result just to give a flavor of what kind of things are known. So there's a theorem of Bobadilla and co-authors, which describes all possible rational degree D curves which have exactly one singularity, which is a cusp, in fact, which is a PQ cusp and no other singularities. Okay, so this is like, these are like curves. So it's relatively restrictive in the sense that we're only considering genus 0 curves with a single PQ cusp and no other singularities. But in that situation, they give a complete list of the possible the possible values of P and Q that can arise, and D. So, okay, so the precise form is not so important, but there's kind of, I guess, 6 different families. Well, I guess the last 2 are just a single curve, but the first 4 are kind of families of curves. But so maybe let me just mention for this talk, so these FIs, FJs, or the FJ is the jth Fibonacci number. So I guess number D plays a particularly special role in this talk, especially given some of the people in the audience. So these are what I call the odd Fibonacci curves. So these are indexed by odd Fibonacci numbers, and there's various constructions of these curves. So I think the most well-known construction is due to Orevkov. So there's in fact, Orevkov even gives multiple constructions of this family of curves. So again, these are just rational curves of degree. The degree is given by an odd index Fibonacci number. They have just one cusp and no other singularities. And for example, Orevkov has a construction given basically by starting out with some very simple curve in CP2 and then applying some sequence of birational transformations to turn it into some more interesting curve with a singularity. Okay, so I'm just giving now I'm just trying to give a kind of a sample of some other sort of types of results that are known. So there's also a theorem due to Orevkov, which says that in the case of a degree D rational plane curve with only cusp singularities, possibly more than one, but no multi-branch singularities, there's some bound on the degree in terms of the maximum multiplicity of a singularity. Or equivalently, you could think of this as saying that as the degree increases, you have to see some point of high multiplicity. Okay. So another sort of very interesting result is so this was actually, I think, a conjecture for quite a while, and then it was proved recently by Koras and Polka. So the conjecture, which is now a theorem, I guess, is that in fact a rational plane curve can have, if you have only cusp singularities, then you can have at most 4 cusps. So they prove this using sort of minimal model ideas from minimal model program, but so a rational plane curve, if you have only cusp singularities, or another way of saying that is that you have a rational plane curve whose image is just homeomorphic to S2, then it can have at most 4 singular points, and in fact it can only have 4 if it's degree 5, and in that case there's just kind of basically a unique representative. Okay, so but in general, so I sort of going beyond these results, there's kind of many open questions about so for example, these are all just results about curves with only cusps. So for example, so in this talk what will be specifically interesting is curves with cusps and some additional ordinary double points. So I don't know if there's much literature already on these curves, and then most of these results are, well, for example, this classification is assuming you have just one cusp. So for example, if you have even multiple cusps, I think there's relatively little known about what types of singularities can occur. Okay, so now let me move on then to kind of one of the other items in my introductory list, which is SFT of ellipsoids. So I'm not going to say too much about SFT in this talk, but let me just mention that so the general sort of object of study will be so you take, so imagine that you have one ellipsoid sitting inside of another, and in fact it's enough to just assume that you can just assume that this is sort of the standard standard ellipsoid in C2. It just happens to sit inside some other larger ellipsoid. And then you can look at the sort of cobordism given by kind of removing one from the other, and you can take the symplectic completion of that to get a kind of a complete symplectic cobordism. And then you can study J holomorphic curves in that cobordism, which are sort of punctured curves with where at the punctures they're asymptotic to Rabe orbits in either the top ellipsoid or the bottom ellipsoid. So this is like at this end is modeled on the boundary of EA prime B prime, and this end is modeled on the boundary of EAB. And in general, in SFT, you would just consider kind of arbitrary curves with some number of positive punctures and some number of negative punctures and some genus in this cobordism. Although there's sort of various levels of SFT. So the sort of the simplest level would be where you're only interested in cylinders, and then the sort of most complicated level is where you just allow arbitrary curves or arbitrary genus, and then there's various sort of intermediate levels of SFT. So for this talk, the most relevant kind of level of SFT is what I would call the stable sector, which is very roughly speaking modeled on genus zero curves with one negative end. So curves that look like this. Okay, and there's some algebraic structure. You can kind of put these together to get some sort of algebraic structure, which is kind of dimensionally stable in the sense that it doesn't care if you cross with c to the n, roughly speaking. So these are the types of curves which would be relevant for these sort of stable embedding phenomena. Okay, and so let me mention so in general, one of the things which makes understanding, so it turns out, for ellipsoids, the general picture is that, so these are contact manifolds, and then this is some symplectic cobordism between contact manifolds. And the general picture is that you assign an invariant to the contact manifolds, and then you assign some sort of map for cobordism between contact manifolds. And in the case of an ellipsoid, just basically for sort of degree reasons, there's nothing interesting going on on the level of ellipsoids as viewed as contact, or the boundary of ellipsoids viewed as contact manifolds. But everything interesting is happening in this sort of cobordism map between two ellipsoids. And one of the things that makes it hard to wrap your head around the SFT in this case is that in general, you can't actually just count geometric curves like this. You have to sort of count SFT buildings. And so making sense of those counts is extremely subtle. But there's certain counts, there's sort of certain distinguished counts which are kind of more well-defined than others. Okay, so for this talk, I want to focus on one specific type of count in here, which is, this generalizes, but this is sort of a count which is kind of robustly defined in this SFT framework without any special consideration. So it's just an honest count of sort of some more injective J holomorphic curves. And the setting that will be relevant for this talk is, so consider the case where you have PQ, two positive integers which are relatively prime, and I'll assume that I'm going to assume that P is bigger than Q, such that P plus Q over 3 is also an integer, which I'll call D. And then you can look at the following count of curves. So this is the top boundary is just the ball, or maybe the slight perturbation of the round ball. So I'll just say E1 plus, and then the bottom end is E1 PQ. And then you can consider the following curves. So these are so these are curves with d positive ends, where d is p plus q over 3, and each of the positive ends are asymptotic to, well, basically to the sort of long Rabe orbit in the boundary of this perturbed ball. And then the bottom end, so L is for the long orbit and S is for short orbit. So the bottom end is asymptotic to the p-fold cover of the short Rabe orbit. So here by short and long, I mean, so we're sort of in EPQ. So there's kind of one Rabe orbit. There's just two simple Rabe orbits, one going around this way and one going around this way. So the one of the one which has which bounds a disk of smaller area is the short orbit, and the other one is the long orbit. Okay, and it turns out, so there's an observation due to several people. I learned about this from Dusa McDuff. So these curves are quite relevant for this stabilized embedding problem, and in particular, they have Fredholm index 0. And moreover, you can show that these curves are sort of robustly defined. So basically, if you pick a generic, almost complex structure, you'll just get some count of these curves, some more injective curves, and then you can show that it's independent of all choices. So independent of, for example, of your choice of almost complex structure. Equivalently, you can also, so a little bit closer to this rational curve picture, you can, this is the same as the count of curves in CP2 minus basically the ellipsoid EQP or E1 P over Q, which have degree D. And so now we've closed up the top end, so there's no positive asymptotic Rabe orbits, but it still has the same negative orbit short to the P. Okay, so you can show that this counts. So this gives you just some sort of numbers, TPQ, which I'm rather obsessed with, and you can show that they're integers. In fact, by sort of a consequence of automatic transversality, they're non-negative integers. So each of these curves counts positively if it exists, and so you get these non-negative integers, and the relevance for embedding problem is that you can show that if there's a non-zero number of these curves, so if there exists at least one curve like this, then there's an embedding, there's a construction due to Hines, so the Hines version of the folding embedding, which is then optimal at that value for x equals p over q. And this is just some embedding which kind of embeds a stabilized ellipsoid into a stabilized ball of some specific size. Okay, and then there would be generalizations of these counts for example, if you want to replace the ball with some other ellipsoid, then you would replace CB2 with some other toric surface. Okay, but I'll just focus on this case for concreteness. And specifically, if you, in the case where Q is even equal to 1, so then it's just T 3D minus 1 for some D, which I also abbreviate these as just TD. So then this is some kind of particularly, in my opinion, particularly natural count. So it's just so now in that case you can basically think of the bottom ellipsoid, the ellipsoid EPQ, as just, and that at that point you can just think of it as being a kind of arbitrarily skinny ellipsoid. And well, we showed with McDuff, we showed that this actually has an interpretation as the count of degree D rational plane curves, just curves in CB2, which have sort of a maximal tangency condition to a generic local divisor at a given point. So it's sort of like an analog of Kontsevic's count of rational plane curves passing through 3D minus 1 points, but now instead of point constraints, you just have a single constraint with sort of maximal tangency condition required, where the tangency is to some generic divisor. Okay, or you could really think of this as just being rational curves where you ask them to pass through a specific point, and then you kind of prescribe as many derivatives as you can at that point. So, first derivative, second derivative, and so on, until you get a Fredholm index 0 problem. Okay, so let me mention also, so in the 4-dimensional ellipsoid embedding problem, there's kind of there's a very beautiful picture due to McDuff, which is basically describing a resolution of the ellipsoid EAB. So the picture is the following. So imagine that you had some, so imagine that the purple thing is some toric surface, and so if you think of this purple thing as the moment polytope of a toric surface, then you would have singular points here and here. So here we've sort of cut out the triangle of the triangle EAB. So this triangle here is the moment map image for just the ellipsoid EAB. And you would, in general, you'll have orbifold points here and here for this toric surface. But then you can resolve those points by blowing up. And the picture is, so here I've just drawn the example. So B is 2, A is 5. So you have orbifold points here and here, and then you can do a sequence of blowups to kind of resolve. So you have this kind of, so this, in the toric surface, this is some divisor with 2 singular points, and you can resolve it by a sequence of blowups. And the idea is that you take a bunch of very small, so after blowing up, you end up with a bunch of very small divisors, and then you'll sort of have one large divisor which has the same slope as the original divisor. So here I've just drawn the sort of outward normals. So in this case, you have to blow up, I guess, 1, 2, 3 times. And so this replaces this singular divisor with a chain of smooth divisors. And in fact, what you're basically showing is that so a convex neighborhood. So this, you can think of sort of the ellipsoid EAB as being kind of giving a convex neighborhood of this divisor, and now you're replacing it with a convex neighborhood of some kind of smooth normal crossing divisor. And in fact, it's exactly the same chain that we had that you see in the resolution of the AB cusp of a curve. So you get sort of this 1, -1 curve, and then these 2 chains here. Okay, so this suggests, I think, rather strongly that the existence of a PQ cusp should be closely related to having a negative end on the ellipsoid EQP. Okay, and so this is just a remark that I mean, this is kind of a beautiful picture. So I described this plumbing has to do with the negative continued fraction expansions of these 2 fractions related to P over Q, and the sizes of these blowups. So each of these blowups, since these are symplectic blowups, they each involve a certain size, and the sizes are given by the so-called weight sequence, the weight sequence of P over Q. And the weight sequence is basically just the let's see, so in my picture over here, the weight sequence is basically the coefficients that occur. So in this case, it would be 2, 2, 2, 2, 1, 1. And these are just given by basically, you start out with PQ, and then you get P minus QQ, and then you sort of keep going until you get something smooth, and then you keep going until you resolve until you get a normal crossing resolution. Or you can think of the weight sequence as kind of giving you this picture here. So 5 over 2 corresponds to 2, 2, 1, 1. And these are also, the weight sequence is also closely related to the positive continued fraction expansion of P over Q. So 5 over 2 has this as its weight sequence. There's 2 copies of the first thing and 2 copies of the second thing, and that corresponds to the fact that the continued fraction coefficients are 2 and 2. Okay, so as I said, I think this strongly suggests that the PQ cusp is sort of interchangeable with a negative end. Has something to do with kind of removing the QP ellipsoid and then looking at negative ends on that. Okay, so let me state this as a conjecture. So so I'm stating this a little bit imprecisely, but a negative end. So specifically a negative end on the p-fold cover of the short orbit in this ellipsoid, or maybe some kind of small constant times this ellipsoid, is interchangeable with a PQ cusp singularity at a point, together with some prescribed derivatives. Okay, so here the remark is that you see when you have a PQ cusp, even though, so the point is singular. So like if you were to parameterize the curve near this point, you would have the derivative of the parameterization would vanish at the origin. But nevertheless, sort of geometrically, if you just think about the image of this curve, it has actually a well-defined tangent line at this point. So if you kind of look at the limit of the tangent lines of the curve as you approach here, in this case, it has a well-defined tangent line, which should just be horizontal. Okay, so then you can ask for, so you can ask for a PQ cusp, but then you can also ask for it to have a specific tangent direction at the point. And you can also ask for sort of specific higher order derivatives, geometric, sort of for the geometric image at that point. Okay, so this is, and this number f p over q is just related to this weight sequence of p over q. So for example, that you should compare this to the earlier statement I said, which is that having a negative end on a cover of the short orbit in the skinny ellipsoid is interchangeable with having a point constraint with n-1 prescribed derivatives at that point. Okay, so then in particular, this would imply that yeah, and by the way, I think that this statement, I'm phrasing conjecture, but I think it can be, well, I could say a little bit about why I think it should be true, and it should be provable using relatively similar ideas to this equivalence, which is basically some neck stretching argument. But in particular, this would imply that this TPQ numbers that I said I'm sort of obsessed with is the count of just the count of degree D rational plane curves with one PQ cusp singularity at a prescribed point, and also some number of prescribed derivatives at that point. And then in addition, you have some number of double points, which are just required by ejunction. So because ejunction formula says that, this singularity contributes something to the count of singularities, and then you need some sort of additional singularities, which are just double points in this case, to satisfy ejunction. So in other words, this count can be interpreted as curves with a single kind of PQ cusp, and then possibly some number of sort of additional double points. And in particular, the extra tangent. So these extra tangent the extra prescribed derivatives are something you would need to get these. You would need these to get the two problems sort of have the same index. But geometrically, if you're given a curve with a PQ cusp, you can sort of fudge a little bit and just choose the directions to be whatever the directions that curve already has as its derivatives. So in other words, if you're just trying to find a curve, you can actually just ignore this prescribed derivatives. So in particular, this says that TPQ is non-zero if and only if there exists a degree D rational plane curve with a PQ cusp. And I'm also using here the fact that if you had any other singularities, you could just replace them with some number of double points. Okay, so now this is something that in principle you could just use classical algebraic geometry techniques, or maybe birational transformations to try to find a curve like this. And again, anytime this is non-zero, it tells you something very strong about stabilized symplectic embedding. So it tells you that this folding instruction is sharp. Okay, so let me give a few examples, kind of illustrating this corollary, and then hopefully at the end I want to state kind of a formula, a new formula for TPQ. But let me first let me give sort of a few examples, which I think kind of illustrate how this corollary might. So it, on the one hand, it could allow you to use kind of algebraic geometry techniques to say things about symplectic embeddings, but also conversely, in principle, you could use this. You could use sort of symplectic techniques to say things about algebraic curves. So, for example, to produce new algebraic curves. Okay, so in the first direction, so going back to these odd Fibonacci curves. So this is the case where PQ is fi plus 1 over fi minus, fi plus 2 over fi minus 2, where I is an odd integer. And in this case, it turns out that there's no additional double points. So this singularity already satisfies Ejunction. So these are just unicuspidal curves. So they have no extra singularities. And it turns out in this case, the count is actually just 1, which is kind of a general, maybe a general phenomenon that when you have curves which satisfy Ejunction, they tend to be sort of unique, very roughly speaking. But so these curves, as I said, they were constructed by Orevkov using some sequence of birational transformations. They were also constructed independently by Christopher Gardner Hein basically using the ECH-cobordism map. And well, either way, so once you know that the count is non-zero, it shows that the Fibonacci staircase of McDuff and Schlenk stabilizes, or at least the sort of first part of the Fibonacci staircase stabilizes, is a corollary of just the existence of these curves. Okay, and in fact, well, Christopher Gardner, Hein, and McDuff went further, and they found another interesting sequence of curves. These are the even index Fibonacci curves. So this is the case where P over Q is fi plus 2. Whoops, sorry. What am I doing? This is the case where P over Q is a ratio of Fibonacci numbers where now the index is even. And they showed that well, at least in this language, the result is equivalent to saying that this TPQ is positive in that case. And in this case, these curves are not unicuspidal, so they have one additional double point. So they have a PQ cusp and then one other double point. And so as far as I know, I don't know if these, so in particular, this gives kind of a new family, I think, of rational plane curves with sort of some relatively simple singularities, which I don't know if these are known in the algebraic geometry literature or not, but.
Kyler, have you actually proved that you get this family? I mean, is this still conjecture?
You prove that you have this family.
Well, I mean, I know we have the curves with boundary on the ellipse, but you wanted to then claim you get this algebraic curve when you fill in cone it off, right?
Yeah. Sorry. So yeah. So this does assume this conjecture, which I think I probably could prove, but I definitely haven't checked all the details. So this is assuming this conjecture.
Yeah, that way round shouldn't be too hard, it seems to me. I mean, if you actually got the curve with the negative end on the ellipsoid, you should be able to sort of cone it off. But
yeah, so you did a lot of hard work to find these curves using symplectic techniques.
Yeah, that's right.
I mean, there are some subtleties in this conjecture because it's sort of like an instance of the symplectic isotopy problem. So, it has the flavor of saying, given a J-holomorphic curve, you need to be able to produce a J-holomorphic curve for the standard integrable J. So you start out with some generic J, and then you have to sort of isotope it to the integrable J and show that the curves persist. But in this situation, I claim that nothing too bad happens. So you can just follow the isotopy.
Yeah, we could start off with something which is pretty integrable, because I mean, this curve is very persistent, the ones we found. So,
Right.
You could start off with an integrable J on the whole of the, and you've got then you've got this little ellipsoid, and then you have to complete it to a negative end, right? So you have to deform it slightly, but not hugely.
Right. Yeah. And the other thing to mention is that like, for example, when you look at these curves with the sort of maximal tangency condition, these can degenerate. These and similarly for this sort of cusp condition. So these singularities can in principle degenerate into some other kind of more complicated singularity, but you can show that these degenerations are all codimension, at least complex codimension at least one, or real codimension at least two. So the degenerations don't really cause you any trouble in a generic one parameter family. Okay, and I just wanted to mention that in fact, this is actually just equivalent to, at least I claim that this is actually equivalent to just some question that's pure low dimensional topology. So TPQ is non-zero if and only if there exists a certain immersed symplectic cobordism. So this is kind of in kind of S3 across the interval between two transverse torus knots or torus links. So this is just so TPQ has kind of a canonical representative as a transverse knot with maximal self-linking number, and then you can also write TDD, but now this is a decomponent link, and so this is actually equivalent to just the existence of a symplectic cobordism with positive double points from one transverse knot to a transverse link, or equivalently from a transverse knot to kind of a capping of it in CP2. So some of these, so if you're quite kind of good at these constructions, at least some of these have been found kind of independently just by hand or by kind of low dimensional topology constructions. So for example, I guess one of the first interesting odd Fibonacci curves is the case where PQ is 13/2. So for example, Josh Sablev has explained to me how you can construct this cobordism using kind of knot techniques, which is quite interesting. Okay, so but anyway, so in the last few minutes, I just want to now state kind of a new formula for TPQ. So it's a formula for TPQ, which I think has the potential to shed quite a lot of light on these questions of existence of algebraic curves with singularities. So let me end by just kind of stating the formula, and I have to state it a bit quickly since I'm almost out of time. But so here's the formula. So basically the gist of it is that you can, so TPQ is, you can compute it as a count of trees in the sense of graph theory, each with D leaves with some combinatorial coefficient, which are a little bit more complicated than I would like, but there's something that's, you can just write down by some formula. So to write down the formula, so to start, I have to introduce this notation IKX So if x is just a real number here and k is an integer, so the pair IKX is the minimal pair. It's the pair IJ whose sum is k and which minimizes the expression. It minimizes the maximum of I and JX. Okay, so for example, if x is kind of infinity, then you would never have J be non-zero. So in that case, you always just have I be k and J be 0. On the other hand, if x is 1 or a little bit more than 1, then it's most efficient to kind of spread out the i's and j's. So then kind of if k is even, then you just take the same number of i's and j's. So k over 2 and k over 2. Okay, so let me let TD denote just the set of rooted trees with D leaves. So a rooted tree. So okay, without those decorations, a rooted tree. So it's just a tree in the sense of graph theory, so it has some. So lead, so there's a root. So there's a root is some distinguished vertex, which we usually write on the bottom with valency 1, and then there's some other vertices with valency 1, which are called the leaves, which appear on top. And you can sort of then orient the edges from bottom to top towards the root. And V, so we can consider the internal vertices, which are, so these are the vertices which basically have valence at least 2. So these are the internal vertices. And then let me denote by V move the so-called movable vertices. And this is just my terminology. There's probably a standard terminology, but I just didn't know what it was. So the movable vertices are the ones which have only leaves above them. So for example, this is not a movable vertex because it has this vertex above it, which is not a leaf. But the red ones are movable vertices. So movable in the sense that you could sort of raise them, you can kind of bring them up or down without running into another vertex above it. Okay, and then, sorry, there's another non-standard terminology. There's probably a better one, but the leaf number of a vertex is just the number of leaves that are ultimately above it. So like this one has leaf number 3 because there's 3 leaves above it. This one has leaf number 5 since all 5 leaves are above it, and so on. Okay, and then let me introduce this one more piece of notation. So kind of number PQ V is, so I define this. Sorry, this is I and J with respect to X equals P over Q. So you basically take some factorial, some I and J factorials, where on top you're looking at sort of this expression's 3 times the sum of the ki's minus 1, and then here you kind of summing over the I of 3ki minus 1 individually, where k1 up to kn are the leaf numbers of the incoming vertices to V. So if this is V, then you look at so in this case, k1 would be 3 and k2 would be 2, because these are the incoming vertices to the pink one, and this one has leaf number 3 and this one has leaf number 2. Okay, so this is just some purely graph theoretic notion with some maybe non-standard terminology. Maybe there's a better terminology, but okay. So then the formula, which is, and this is based on joint work with Grisha Mikalkin. So the formula is the following. So well, yeah. So it's this expression here. So it's a sum over trees with D with D leaves. So remember that D is P plus Q over 3. And T is the number of automorphisms of a given tree. So for given a tree, you can talk about as automorphisms. And then it involves these expressions, number P over QV. So you take a product of some coefficients for all internal vertices, and then you also take a product for all the movable vertices of some expression like this, which involves, 2 leaf number V choose leaf number V, and this is 2 to the minus leaf number V, and so on. And so overall, you'll get 1 term for each tree with D leaves. Okay, so maybe, so I'm already a little bit over time, so maybe let me just end with this formula. And yeah, thanks. So thanks very much for your attention.
Tyler, so is this formula based on your analysis of this sort of, from SFT, you get this Lie algebra structure and that recursion formula you had there? I mean, is this?
Yeah, it's related to yeah. So in an earlier work, I had a different kind of recursive formula for TP over Q, which was much more complicated than this one, and this is kind of, you could prove this using that formula, but with some. So actually, it's actually not hard to prove this formula from that one, but somehow finding this formula required some new geometric input, which is basically has to do with the counts of descendant curves in the ellipsoid.
And does this always give you a positive number?
Yeah, so that's kind of the question. So unfortunately, you have these signs, which you have this sign which depends on the number of internal vertices of the tree. So it's not, yeah. So at this point, it's not yet clear when these give positive numbers, although it's getting maybe a bit closer. There's one thing that's really mysterious to me, which is that so in the special case of just TD, where so Q is equal to 1, the first few values of this just gives exactly the number of trees with it just gives exactly the number of trees with ordered leaves, which is of course a positive number, but somehow this formula reproduces that count, but using signs. So
I have a question. Can you go back up a little bit? You had a statement about finding symplectic cobordisms between torus knots.
oh yeah, I think it was this
Right
room.
there, yeah.
Yeah.
Okay. Could you? So TP, I know what TPQ is. It's a PQ torus knot, and TDD. Is that like D copies of what's TDD?
Yeah, TDD is like D copies of the knot, but linked in the way that D hop fibers would be linked.
I see. So, and positively immersed symplectic cobordism, that just means symplectic with positive self-intersections?
Yeah, positive self-intersection, so that the kind of curve which could be J holomorphic.
Okay, so at least I'm not exactly sure about these ones, but at least for some pairs of torus knots or torus braids, there is a way to get cobordisms like this, because in my papers with Toms from a long time ago about gluing the holomorphic curves, like the sort of negative ends of one holomorphic curve that you want to glue describe one torus braid, the positive ends describe another one, and then we can glue those, and then when you glue them, that the holomorphic curve between them is the kind of braid we're talking about, the kind of symplectic cobordism we're talking about.
Right. Yeah, well, yeah, I would definitely be interested in talking more. I mean, it seems that somehow, yeah, it somehow how to say, like the tricky, yeah, the at least so far for me, the tricky thing about making that work is like you would like to kind of, sorry, I'm having a horrible like sun in my eye issue right now. This strategy could very well work, but a lot of times the kind of building block curves that you would want to sort of pre-glue together to get these things involve some kind of buildings, which then makes it difficult to kind of use them as building blocks. But anyways, yeah, but we should chat more about that though.
Yeah, we can talk about that later. It's a local picture. You just need any example of curves anywhere, and then you can make this thing.
There's some question in the chat. Mohammed, do you want to speak up?
Yeah, so is there by any chance possible that this formula comes from some localization calculation once you interpret this count algebraically?
Yeah, that's a great question. So you could interpret right, you could interpret in fact, you can also interpret this as some sort of relative Gromov-Witten invariant with some relatively complicated, I mean, with some sort of complicated divisor, which looks like this, which is kind of not regular. It has sort of, negative index curves. Or maybe you could just directly kind of interpret this on the level of curves with cusp. And indeed, it could be the case. So yeah, I don't know the answer to your question, but it could be the case that localization gives you some other way of computing this, which might be related to this tree formula. But I would be very interested in seeing what kind of thing that gives. But
Thanks.
I mean, my intuition is that generally localization gives much more complicated tree counts than this, but I could be wrong.
I have a question, Kyler. Maybe I missed it when you say, so is it right to say, I mean, you talked about resolutions of singularities, plane curves, and then you talked about use of sort of divisor resolution. So are they exactly the same coefficients that appear? Like this weights in the diagrams?
Yeah, the resolution, yeah, yeah, you see sort of the same coefficients appearing in the resolution of a cusp point on a curve and the resolution of the singularities on the ellipsoid of the toric surface.
And this is your motivation for your conjecture of why counting basically curves in this cobordisms with suitable singularities should agree with the negative n version?
Yeah, I mean, this is one, at least this is one suggestion that there should be some close relationship between this negative n count and this cusp count, since kind of, yeah, I mean, the idea for proving the conjecture would basically be that so where is it? So yeah, so you can relate. So on the one hand, you're looking at curves with some negative n, then on the other hand, you're looking at curves with some singularity, but you could relate both of them to some third thing, which is curves in a blow up. So basically it's just smooth curves in a blow up with some sort of homology class given by this weight sequence of P over Q. And so that serves as some intermediary that sort of relates to both of those things. So basically on the one hand, you have given a cusp, you can sort of resolve it and get this chain of curves for this smooth curve attached to some chain of spheres. On the other hand, then you can next stretch along the boundary of an ellipsoid to convert that into a negative n.
And do you know what this function f would be? Or
yeah, the function f is it's basically the number of terms in the weight sequence which are not one, I believe. So it's something you can just write down basically from the weight sequence of P over Q, which is like, kind of related to the continued fraction coefficients. Yeah. For example, so for example, in the case of the ordinary cusp, so that's just 3 over 2. So in that case, you would prescribe. So in that case, you would have to prescribe exactly one derivative. So you would look at curves with an ordinary cusp passing through a specific point, and also with the prescribed tangent line, and that would correspond. Yeah, I could explain this in more detail maybe later, but so the ordinary cusp would then correspond to sort of a curve with a negative end on the ellipsoid E23, where this is the third multiple of the short orbit, and this is with so this is with kind of prescribed tangent line.
okay. Any other questions?
Carla, did you check so you look at curves in symplectization? So we do so when we prove the staircase, we produce curves in the blow-ups of CP2. So then when you blow down, you get curves in CP2, and they should probably correspond to the ECH curves under your conjecture, no? Or is it obvious or wrong? Or you know what I mean? These special classes that we represented by, to get the hard part in the staircase, we just guess certain -1 curves. But they live in a multiple blow up. But then when you blow down, you get curves in CP2, right? But singular.
Yeah. So I think that I think that the curves. I think indeed your Fibonacci, your odd index Fibonacci curves they should blow up exactly. They should blow down exactly to this odd index.
To the one you
Fibonacci curve.
find
Yes.
by checking conjecture with respect to these CH curves that are used in the stable problem, right?
Yeah. So I think indeed, yeah, using the techniques from your techniques with DUSA would be, I think, yet another way of seeing the existence of these curves.
But the difficulty is when we blow up, I mean, we blow up at lots of different points because we have lots of exceptional divisors, right? So if you simply blew down at those points, what you get is a curve which goes through, you've blown up 10 different points. You get curves going through those 10 points with certain branch multiplicities. You know, certain number of branches going through those points. So it's a different thing. You have to then bring all those singularities together into a cusp. I mean,
Yeah.
They are not in this class, right? Okay.
so they're not, it's not an immediate thing. If you have a curve which is in CP2, you know, with some coefficient of the divisor, you know, the sum of KI, or something, and blow down the EI, you get lots of different points. So it's a different, I mean, the claim is the account is the same. The curves are definitely the same, right? I mean, the end result. But, you know, the thing is that all these algebraic geometers, I was looking at this with Kyler a tiny bit, and the algebraic geometers just look at the problem when there's one cusp and no other singularities. And what we're interested in is finding, you know, curves with double points. And they don't look at that. So they don't look at curves with arbitrary numbers of double points sprinkled around plus a single cusp singularity. And so there's no analog of the result that I proved about the ghost staircase with Hind and Christopher Gardner, about that you have one double point. And it's likely that that result can be translated into new existence of new algebraic curves, but not known yet. And that was such a hard calculation. I mean, obviously you could, that method would extend to ones with 3, you know, the next thing, but you know, you start off with 640 or something curves, which is the Gromov-Witten invariant, and then you have to figure out all the possible things that might happen to it. One could do that with enough persistence, but it doesn't seem a good method in general, unless you can find some of these magic recursion things that Kyler finds that would help you make a calculation, show something is left positively at the end.
Any more questions or comments? Okay, I think we can take, oh, is there any other question?
Well, if there's no questions about the talk, I told Kyler I had a question for him, somewhat related. Yeah, so I'm a complex analyst and interested in knot theory and symplectic topology. Now, when it comes to quasi-positive knots, you know, for me, I think about boundaries of analytic varieties. So I was wondering about this question, and well, a little bit of correspondence told me the answer wasn't known. I could be wrong. Let's say I ask for degree n, how many different types of quasi-positive knots could I get with polynomials of degree n?
Can you explain what's a quasi-positive knot?
So quasi-positive knot is, if we're talking about knots in the boundary of the two-wall in C2, okay? So one of two ways of describing it. For me, it's isotopic to the boundary of an analytic variety. And then due to work of Rudolph and Arefkoff, it's also has a description in terms of presentation of knots. I think it's a product of conjugates of positive terms, something like that. You know, if you're saying how many knots, take degree 10. Let's look at polynomials P of ZW equals 0. Let's suppose that I actually got a single curve there. I mean, there's questions about links too, but I could say how many different quasi-positive knots could I get with polynomials of degree 10 or degree n. And
I see. Yeah, so that's sort of like almost like a generalization of the questions I'm mentioning, where you're, instead of just considering, you know, PQ torus knots, you're allowing kind of basically like more complicated iterated torus knots.
yeah, it looks closely related. But it's not so much about the type of singularity. But there's nothing like that. Is that accurate?
I don't know of any results like that, but
Yeah. So I discovered after a while that I had some questions which might be new, but like this one in particular, it's beyond me. So I just share it when it's seems like somebody might be interested.
Guys, if you don't mind, I think we can thank Kyler again for the talk and leave any other questions for discussion. So thank you, Kyler.